Hello all, today we will work on this section 15.10, and I believe very likely when you first watch the videos, the lecture videos, you may still get confused about the change of variables. So before I start going over this section and do some problems, let's review a little bit. Okay, so what usually happen is we have a domain which is ugly, and we call that S star, the ugly one, ugly domain on XY plane. And because the domain is too ugly, then we need to reshape that, right? Okay, now the thing is, like, when we reshape that, we basically need to think about what kind of domain in UV, which is good, the good shape, such that using transformation T, we get that ugly shape. That's the one kind of like, how to say that, not really natural, because what we usually do is we transform from the ugly one to the good one, right? This is what we usually do. Okay, from ugly domain, we reshape that into good domain. Now that's the one we call T inverse, the inverse transformation. Okay, the way our textbook teach us is that the transformation T that we have actually coming from the good one to the bad one. Okay, now, so I hope you keep that in mind, that when we work in these sections, which one is a good one, which one is bad one. Okay, now the good one will be in UV. I'm sorry, I write it wrong here. It should be V here. And the bad one, the ugly one, will be in XY. Okay, now we will go through these sections. And I try not to go fast. You will see I actually do more problems like odd numbers, not only even numbers. In my lecture videos, I already did sufficient even numbers, but I think if we want to do more, I cannot avoid doing some odd problems from here. Okay, let's start with number 7. Number 7. Find the image of the set S. So the set S is the starting point. Okay, notice that the S here is in terms of UV. Okay, where the U is from 0 to 3 and the V is from 0 to 2. Honestly, if this were our starting domain, that is too nice, very nice. Why? Because it's already a rectangle, right? I don't think we want to take this away. But no, this is not the one they want. This is the good one, right? Okay, the question is find the image of this set under the transformation. So we want to find using transformation T. So remember, we come from the good one. Using transformation T, we will get the ugly one. Okay, so they tell us the transformation, how to make this set S becomes ugly. Okay, now with the transformation T to be X equals to 2U plus 3V and Y equals to U minus V. Now there are many ways to do this kind of thing, to do this transformation. I think I will start with point-to-point transformation. In other words, I will start with all those corners, okay, and we will get the coordinates in XY terms, in XY plane. Okay, so the transformation of 0, 0 in UV, when I plug that u equals to 0, phi equals to 0, the xy will be 0, 0, right? So if I call this point A here, this will be the image, A star. Okay, the transformation of 3, 0, if u equals to 3, x will be 6, and y will be 3. I plug that in here. Okay, so 6, 3, let's say this is 1, 2, 3, 4, 5, 6, up 3, 1, 2, 3. So this is the image of B. This is B star. Okay, and then how about T02? When U phi is 02, and then the X will be 6, -2. Okay. Let me put it here so that I know 6, -2 here. So this path, let me use different color. This is my first path here. Call that gamma 1. Here later on becomes, this path also becomes, this is the path, the shadow of gamma 1. Actually, there's a big question about Thomas. How do we know that it will be a straight line? Actually, we don't know yet. But if you take a look, that the transformation we have here are all linear transformation. It means it will transform line segment to line segment. Okay, but I will explain that a bit further later on. Now, let's go with that first, and then this is gamma 2. You know what? Instead of using gamma 1, gamma 2. Let me just choose play with the arrow. So this is my second path, arrow 2. Okay, and this is my C star from C. And then, no, that's not right. Actually, oh, I'm sorry, that's not right. That's not right. That's not right. Actually, this is my C. This is my C02, right? This is my C. Yeah, that's my C. Call this second arrow then, or third arrow. So it will be this one here. Okay, now and then coordinate D, which is 3, 2. Okay, transformation of 3, 2. What will the x be? 3 and 2, that will be 12. And then 3, 2, that's 1. So approximately here. This will be our 2 arrows path, right? And if we call this the fourth arrow, the fourth path, it will be like this. Okay. Now, of course, this technique, the point-to-point transformation, give us only the points, but it doesn't give us the path. Okay. Now, if we want to refine what we do here, we go on with the path. Let's say the first path. Let me give myself some space here. The first path, okay, so I need to call this first path. The first path, gamma 1, that's the u from 0 to 3, but the phi equals to 0, right? Now you plug that into the t. We plug that into the t. So what happened is x will be, if phi equals to 0, x will be 2u and u. Okay, notice that it becomes parameterized by u, right? So basically coordinates x, y along this path is parameterized by 2u, comma u. Okay, when u equals to 0, it's 0, 0. When u equals to 3, that will be, when u equals to 3, it will be 6, 3, right? Okay, now that's for the first path. The second path, which is so call this second path here. The second path, u equals to 3, but the v will be from 0 to 2, right? Okay, so under that transformation, x will be 6 plus 3v. The y will be 3 minus v. So you see the coordinates is being parameterized by 6 plus 3v, 3 minus v, where the v is from 0 to 2, right? When v equals to 0, we get 6, 3. This is 6, 3. And then when the v equals to 2, we get 12, 1. Right? And you can see this is the parameterization of a line segment. Okay, how about gamma 3? Gamma 3, we have, this is gamma 3 here. That's when u equals to 0. And then the v is from 0 to 2. The xy becomes 3v negative v, right? Such that the coordinate xy now becomes 3v negative v. When v equals to 0, that's 0, 0. When v equals to 2, we get 6 comma negative 2. Okay, and you can also see gamma 4, for example. Gamma 4 is when v equals to 2, but the u from 0 to 3. Okay, so x is, the v is 6 plus 2u. The y will be u minus, I'm sorry, yeah, u minus 3, huh? So the coordinates will be xy equals to 6 plus 2u negative 3 plus u. Oh, I'm sorry. The v is 2. The v is 2, not 3. The v is 2. Yeah, once I compare with the graph, I know something not right. The v is 2. Okay. And that gives us the fourth path, and we confirm the paths are straight lines, line segments. Okay, now this is one example of like from a good one to ugly one. Now, if I want to continue from here, suppose, I hope you remember, suppose I want to find my Jacobian of t, that is the discriminant of dou x dou u, dou x dou v, dou y dou u, dou y dou v. Okay, which will give me negative 2 minus 3, which is negative 5. However, the one we put into the integration later on will be absolute of the Jacobian of t. Okay, that's just to set up for our future reference. Let's go on. That's for number 7. Let's try number 9 now. Number 9, S is the triangular region, of course in U and V, right? With vertices 0, 0, 1, 1, 0, 1. Okay, 0, 0, 1, 1, 0, 1. The transformation is x equals to u squared, y equals to v. Okay, so what will happen on xy plane? What will that guy happen? We can first transform coordinates. Okay, so when we plug in u equals to 0, v equals to 0, the output will be 0, 0. Okay, so if this is 0.0, this is 0 star. Okay, how about 1, 1? Oh, the same thing, huh? T11 is still 1, 1. Okay, and then how about T01? T01 will be 0, 1. Oh, the same, 0, 1. Oh, okay. The thing is like, are they? Will that be triangle again? The thing is we have this u squared, right? So it's which is not a linear transformation. So we need to slow down a little bit. Okay, let's observe, for example, this is the first path here. Okay, let's observe the first path, gamma 1. That is u equals to phi, huh? That's the equation, u equals to phi, right? U equals to phi. So what happened with the xy? What happened to that path? If u equals to phi, well, x equals to u squared. Okay, but y also equals to u. That implies x equals to y squared. Is it right? Now x equals to y squared is this path here. Okay, so it's curved now. Okay, it's curved. And then how about gamma 2? Let's say this is our gamma 2. Our gamma 2 is when our phi equals to 1, but our u is moving from 0 to 1. If phi equals to 1 means the x will be 1. I'm sorry, the y will be 1, right? But the x is moving as a u square, right? But the y is equals to 1. The y equals to 1 is basically this line. Okay, it will be that line. And then gamma 3, we have u equals to 0. The phi is, this is gamma 3 here, the third path. The phi is from 0 to 1. So the x will be 0, the y will be just equals to phi, which is from 0 to 1, right? So it is still just a segment. Right? Now, so if we look back, which one is our S? This is our S, and this is the ugly one, the image. This is our H, S, this is our image, the ugly one. Okay, in reality, when we do the integration later on, we should find, we should transform from this ugly one and go to the good one. Okay? That's for number 7 and number 9. As for the Jacobian, I think you can just do it yourself. Let me just do it. Why not? So, in case we need to do the Jacobian, then the Jacobian of t will be the partial of x respect to u, partial of x respect to phi, partial of y respect to u, partial of y respect to phi. So this will be 2u. Okay. Now let's go on. I believe we did number 12. Let's try number 11 then. Okay, let's try number 11. Now you will see this in this section, in this part here, the challenge is increased. Okay, number 11. you have R is bounded by y equals to 2x minus 1. This is y, this is x, 2x minus 1. Let me use different color. Yeah, I still use this one, 2x minus 1, approximately like this. This is 2x minus 1. And then y equals to 2x plus 1. So there must be a parallel lines. And then y equals to 1 minus x. Y equals to 1 minus x. And y equals to 3 minus x. So I'll go up 2 units. This is y equals to 3 minus x. So this is our r here. Let me use a thicker color so that we can see better which r we are talking about. Now remember, one of our technique earlier is to move, do the transformation from point to point. Okay. Now here the question is find the transformation. Find the transformation equations of a transformation that maps a rectangular region S in UV plane onto R. So we need to find a transformation. We need to find a transformation from UV plane, the good ones. We want that to be a rectangle that maps to that ugly guy, which is kind of strange, huh? Okay, but you will see the idea behind this later on. If we know how to make it ugly, then inverse transformation of that will be the one make it nice. Okay, now if you watch my lecture videos, you will see that we actually have many possible such transformation. But if you notice that the boundary here, y equals to 2x minus 1, y equals to 2x plus 1, seems like we can play with that. Okay, we can make it 2x minus y, call that u. Okay, now why you do that, Thomas? Well, because when I have y equals to 2x minus 1, I can rewrite that into 2x minus y equals to negative 1. Y equals to 2x plus 1, I can rewrite that as 2x minus y equals to 1. Okay, so if I substitute this guy as my u, then you will see the u will be between negative 1 to 1. Right? Now, likewise, so let me mark that in yellow. And then the other one, I will mark that in blue. Okay, do you see the pattern? Right? If I use x plus y equals to 1 and x plus y equals to 3, right? You know what? I write the question, initial situation first. So I have y equals to 3 minus x and y equals to 1 minus x. I can rewrite each one of them to be x plus y equals to 3 and x plus y equals to 1. So we have good reason to believe that, you know what, if I do the substitution, sorry, my color is not good, x plus y as my v, then later on my v will be moving from 1 to 3. But that will give us the rectangle by doing substitution. Okay, so let's use that. So I will do this substitution. U equals to 2x minus y and v equals to x plus y. Now notice this transformation actually starting from xy going to uv. Right? So this is not the t. This is not our t. This is our t inverse. This is our t inverse. Maybe I use different color. That's our t inverse. because the input is xy, the output is uv, right? So T inverse is this guy here. Okay, but at least from what we draw there, we see that our u will be from -1 to 1. Our u will be from -1 to 1. And our phi will be from 1 to 3. Okay, so -1 to 1 and then 1 to 3. So -1 to 1 and this is from 1 to 3, like that. Okay, that will be our S in uv. Okay, we still need to answer the question though, what's the transformation? Now that transformation T that we are looking for is basically reversing this process here. So using xy, we have xy uv in terms of xy. Now we need to change xy in terms of uv. Okay, so one way to do that, I can add this. When I add this, I get u plus v equals to 3x. So my x will be 1/3 u plus v, right? Okay, and then you can substitute this in right away to either one of those. Maybe I substitute into the second one. Phi equals to u plus v over 3 plus y. So y is negative u over 3 plus 2v over 3. So that's 1/3 negative u plus 2v. Okay, we can also do it this way. The idea is you do, if you remember in algebra 1, we solve for y, right? We already solve for x here, right? So to solve for y, I need to eliminate the x, so I multiply this by 1, multiply this by -2. So I get 2x minus y equals to u, and then -2x minus 2y equals to -2v. When I add, I get -3y equals to u minus 2v. So y equals to negative u over 3 plus 2v over 3, which is what we get earlier. Okay, so now we get the transformation that we need. Now, just to remind you, suppose we need to compute the Jacobian. Suppose I need to compute the Jacobian. Jacobian of t, because it's linear transformation, is easy to see. That's 1/3, 1/3, negative 1/3, positive 2/3. You will get 2 over 9 minus negative 1 over 9. That's 3/9, which is 1/3, right? Okay, but suppose I don't need to find the transformation t. Can we find the Jacobian of t without finding the t itself? The answer is yes. It is by finding the Jacobian of t inverse. The Jacobian of t inverse will be 2, -1, 1, 1. That is 2 minus -1, which is 3. So the Jacobian of t, so from here, Jacobian of t is 1 over Jacobian of t inverse. Okay, which is 1/3. Now you see that we get the same thing. Okay, that's for number 11. So the challenge in this number 11 is like, can you find the transformation while that's the thing that we actually get before, right? They give us the transformation before. Now we need to find the transformation ourselves. That's more challenging, of course, but hey, we get there. Okay, number 13. Number 13, R lies between circles with radius 1 and oh, okay, this is radius 1, this is radius radical 2 in the first quadrant. Oh, okay, so so we have something looks like this then, approximately, right? That's our R, which is, they call this ugly, even though in my opinion, this is actually pretty nice. In fact, if you remember, if we have any domain that looks like this and we need to do the integration, we will do it by converting it to polar, right? Okay, now that's what we're gonna do here. If we convert that to polar, I think then I will use the radius from 1 to radius to radical 2 and the angle theta from 0 to pi over 2, right? Basically, the transformation that we use will be x equals to r cosine theta and y equals to r sine theta. I wonder if you remember that. We are basically done. Okay, we're basically done. That gives us the nice one in the first quadrant. Let's say this is r, this is theta, so my r will be from 1 to radical 2 and the theta will be from 0 to pi over 2. Okay, this is our S, the nice one. That one happens to be on the easier side. But I hope you also realize that when we convert the double integral using polar coordinate system, okay, from rectangular to polar, okay, then you will see we actually change the boundaries, the limits of integration becomes constant, and therefore we end up with a rectangle. Okay, can you guess what is the Jacobian for this t? The Jacobian for this t is dou x dou r, that's cosine theta, dou x dou theta, that's r negative r sine theta, dou y dou r, that's sine theta, dou y dou theta, that's r cosine theta. It's too close, huh? And that is equals to r cosine squared theta minus negative r sine squared theta. To our surprise, we get r cosine squared theta plus r sine squared theta, which is just r, right? And if you remember, when we do convert from rectangular integration to polar integration, in rectangular, and we convert that to a polar, we have extra r here. We have r dr d theta, while here maybe we have just dx dy or dy dx. Remember that? Now that r here is the Jacobian that we have. In the past we just called it r, right? Now we have explanation that r that we did by picture at that time is actually being confirmed using another technique under this Jacobian idea here. Okay? Okay, let's move on. Number 15. Use the given transformation. Oh, that's nice. They tell us the transformation, huh? Use the given transformation to evaluate the integral. So number 15, I remember we did number 16 in my lecture video. So let me do number 15 and 17. double integral over region R of x minus 3y dA, where the R is the triangular region 0, 0, 2, 1, and 1, 2. Dang, that's so ugly. With the transformation x equals 2u plus phi and y equals to u plus 2 phi. If you want to do the Jacobian now, go ahead. That's 2, 1, 1, 2. That will be 4 minus 1. That's 3. Okay. Now the thing is, what is the u phi? What is the domain in u phi plane now? That's linear transformation. So we can just do the spot transformation, 0, 0. So transformation of, oops, sorry. Now we need to find what is the u phi such that it gives us 0, 0, right? Is it right? Oh, you know what? Let's do it this way. Let's find the t inverse instead. Let's find the t inverse. So if I multiply, let me write it down first. So 2u plus phi equals to x, and then u plus 2 phi equals to y. If I want to find the u, I will kill the phi. When I add, I get negative 3u equals to negative 2x plus y. So u equals to 2 over 3x plus 1/3 y. If I want to find the phi, I will kill the u. I multiply this by 1 and multiply this by negative 2. Negative 2u minus 4 phi equals to negative 2y. When I add, I get negative 3 phi equals to x minus 2y. So phi is, I'm sorry, this should be minus here. Phi is negative 1/3 x plus 2/3 y. This way, then my t inverse u equals to 2 over 3x minus 1/3 y, and my phi will be negative 1/3 x plus 2/3 y. So when x equals to, when the coordinate is 0, 0, the u phi is 0, 0. Okay, when the xy is 2, 1, what happened to the u? 2, 1, that's 1, 2, 1, 0. So that's 1, 0. 1, 2 will be 1, 2, there will be 0 here. 1, 2, there will be 1 here. So 0, 1. So this is the new region. Okay, this is the R. This is the S. Okay, at least now we have a new domain. Okay, what happened to the integral then? Let me continue below this. So we have double integral over R, region R, of x minus 3y dA. 3i dA. Let's see first. What is x minus 3y? X minus 3y becomes 2u plus v minus 3y. 3 times u plus 2v. That will be negative u minus 5v. Is it right? Okay, so this will be double integral over domains S right now, not R anymore. And then in the integrand we have negative u minus 5v. Now don't forget to multiply by the magnitude or the absolute of the Jacobian, in this case already positive 3. Okay, dA in terms of S, the good one. Okay. Now, which if we go further, then you will see I can factor the negative 3 out. The u will be from 0 to 1, and then the phi, as you see the picture there, the phi will be from 0 to 1 minus u plus 5 phi d phi du. And I integrate it from there. Okay, and then you integrate from there. Let me do it then. This will be negative 3 integral from 0 to 1 u phi plus 5 over 2 phi squared from 0 to 1 minus u, which will give us, let me go to the right, this will be negative 3 integral from 0 to 1 of u times 1 minus u plus 5 half 1 minus u squared du. That is negative 3 integral from 0 to 1 u minus u squared plus 5 half. Give me a second. 5 half minus 5u plus 5 half u squared du. Combine like terms. That will be 3 half u squared minus 4u plus 5 half du. That will be negative 3 times, this will be 1 half minus 4, minus 2 plus 5 half. That's negative 3, huh? I'm sorry. That's my number 15. I plan to do number 17 too, that's why. Okay, number 17, we have the region R. Our R is given by 9x squared plus 4y squared equals to 36. What does it look like? If I divide by 36, that will be x squared over 4 plus y squared over 9 equals to 1. So it is an ellipse, center at origin, with x vertices negative 2, 0, 2, 0, and the vertices on the y-axis is 3, 0, 3, and 0, negative 3. So that's what it looks like. That's the R. Okay, and then the transformation T is x equals to 2u and y equals to 3v. I can just substitute this in to the boundary of R. Okay, so 9 times 2u squared plus 4 times 3 phi squared equals to 36. 36 u squared plus 36 phi squared equals to 1. 36, so u squared plus phi squared equals to 1. Okay, so the boundary of the new one is a unit circle in u phi. If this is in x, y, this is in u phi. Okay, what happened with, oh, you know what? We need to do the Jacobian. How about the Jacobian of t? Jacobian of t will be 2003, that's 6. Okay, now double integral over region R of x squared dA now becomes double integral over region S of x squared becomes 2u squared times the absolute of the Jacobian dA in S. So this will be 6 times 4, that's 24 double integral over S of u squared dA in region S. Then how do I do that? You know what? I polarize this. I will polarize this. I will do double integral in terms of polar. So 24 integral from 0 to 2 pi, integral from 0 to 1. The u, which behaving like an x, right, will be r cosine theta squared times r dr d theta. Okay, you can just integrate it as usual if you want, you know. Okay, so this is 24 integral from 0 to 2 pi of cosine squared theta d theta integral 0 to 1 of r cubed dr. So that's 24 times 1/2 times 2 pi times 1/4. Okay, that we get 6 pi. Okay, that's for number 15. Let's go on. The 17, I'm sorry, not 15. Let's go on. Number, did I do number 26? Should I do just number 26? Let me do number 26 first. Number 26, we have double integral over region R of sine of 9x squared plus 4y squared dA, where the R is the region in the first quadrant bounded by 9x squared plus 4y squared equals to 1. 9x squared plus 4y squared equals to 1. That's 9 squared over 1/9 plus y squared over 1/4 equals to 1. So it's 1/3 here, it's 1/2 here. That's the region R. I think I will do this. You see, to make it unit circle in the first quadrant, my plan is to switch to reshape this, deform this into the first quadrant of unit circle, which basically the x will be extended by 3. Sorry, I write it wrong. So the u will be 1/3 x. No. U equals to 3x. Right? We structure that by a factor of 3, and then the phi will be 2x. Is it okay? I'm sorry, 2y, not 2x. but this is domain xy to u phi, so this is T inverse. This T inverse is from here to here. Yeah, because the input is xy, the output is u phi, right? Okay. Now then, with this transformation, you will see we get double integral over region S now of sine. I wonder if you can see it. Sine u squared plus phi squared. I don't know the Jacobian yet. Leave it there, and then DAS. Now to find the Jacobian, let's say Jacobian of T inverse will be 3002. That's 6. So the Jacobian of T will be 16. Yes. Okay. Now if I polar this further, I make it into polar, then I will get 1/6 integral from 0 to pi over 2 integral from 0 to 1 of sine r squared r dr d theta. Okay, independent of theta, so that will be 1/6 times pi over 2, and then integral from 0 to 1 of r sine r squared dr. This is where we do substitution. Don't use u, you don't use v anymore because we have that already. Let's use w. So dw equals to 2r dr. Okay. So this is pi over 12 integral from 0 to 1 sine w. R dr is dw over 2. Negative cosine w from 0 to 1. So this will be pi over 24, 1 minus cosine 1. Okay. Now, we may come up with another transformation. Remember I told you that the transformation is not unique. Another way. Let me do it here. Number 20. I suddenly just realized that. We don't need to make it unit circle. We can, but you don't have to. If you take a look on the integrand of sine 9x squared plus 4y squared dA, right? You may want to use this substitution instead. You know what? Let me make my x equals to 1/3 u. No. My x to be 4u and then my y to be 3 phi instead. You see what happened when we do this substitution? When we do this substitution, okay, then our 9x squared plus 4y squared will become 36u squared plus 36 phi squared. Okay, that's what happened. That's what happened. Okay, so the double integral over the new region S right now. If I call this S here, let me call this S1. Okay, this is equals to 1. So it is actually a circle with radius 1/6 in the first quadrant. Okay, that's a circle with radius 1/6 in the first quadrant. Now we have sine of 36u squared plus 36 phi squared. Okay, what happened to the Jacobian? Jacobian of t, you will see that's equals to 12. So I multiply by 12 here. Okay, and then dA in S1. This is our S1 here. That is 12 integral from 0 to pi over 2 integral from 0 to 1 6, not 0 to 1, of sine of 36 times u squared plus v squared 12 times r dr d theta. Oh, I'm sorry, I already pulled the 12 out. Okay, so this becomes u squared right now, r squared right now. That's 12 times pi over 2 times, if w equals to 36r squared, dw will be 72r dr. The integral from 0 to 1 6 sine w r dr will be dw over 72. Okay, this 1 6 1 12 pi over 12. Okay, and then the sine w will be, oh, hold on, if I plug in 1 6 square, this becomes 1. With that substitution becomes 1. So gedebam, you will see this is 1 minus hold on, am I missing something? Here, this should be 2 to make it 36. There should be 2 to make 30. So this will be 6 here. So this will be 6, this will be 6, this will be 6. Now I get what I want. Yeah, I copied it wrong. You know, like 2u being squared is 4u squared times 9 give us the 36, right? Okay, so 1 minus cosine 1, as we wanted earlier. That's for number 26. You know what? I see number 25 is being highlighted. Let me copy paste that first and then work on that. And if I think I still have time, I will do number 27. Let's take a look on number 25. Oh, let's see. The R is, the good news is it is in the first quadrant, huh? So the R is 1 0 2 0 0 2 and 0 1. Oh, that's what it looks like. It looks like this. That's the trapezoidal region. If we take a look on this line here, this line is x plus y equals to 1, and this is x plus y equals to 2. We have that x plus y here, right? So let's make it one of our variable, okay, one of our substitution. So u equals to x plus y, and our u later on will be from 1 to 2. Okay, now the problem is then, how about these two lines here? These two lines here. One of them is y equals to 0, and the other one is x equals to 0. I'm thinking to use this as our v. Let's use that as our v. Suppose I give it a try first, okay? And I hope we come up with something nice. So if our v equals to y minus x, Okay, knowing that u equals to x plus y, then when I add this, I get u plus v equals to 2y, right? So y is equal to u plus v over 2. Now, knowing that one of the boundary is y equals to 0, so u for y equals to 0 implies u plus v over 2 equals to 0, implies u equals to negative v. So far our u is from 1 to 2, okay, and then so this guy here becomes this, right? This guy here becomes this. This guy here, let me color it differently. This guy here becomes y equals to negative x. V equals to negative, u equals to negative v, so it becomes this. And you will see x equals to u minus v over 2. So if I subtract this instead, let me write it properly. U equals to x plus y, v equals to y minus x. When I subtract, I get u minus v equals to 2x. So x equals to u minus v over 2, which if I set equals to 0, I get u equals to v. U equals to v will be this part here. So the region that we are talking about, the image in the nice place looks like this. Okay, if this is our R, this is our S here. Okay, how about the Jacobian? Jacobian of T inverse, this is our T inverse, right? Jacobian of our T inverse will be absolute of 1, 1, negative 1, 1. So that will be 1 minus negative 1, which is 2. So Jacobian of T will be 1/2. Okay. Now this double integral over R, you see with the setup is so long, huh? I just do the transformation so far. So double integral over region R of cosine y minus x over y plus x dA. After change of variable, it becomes double integral over region S of cosine phi over u times 1/2 dA in region S, which is integral from 1 to 2 from negative phi to phi cosine phi over u 1/2 d. You know what? The u is outside, the phi is inside, so it must be from negative u to u. Like that. Okay, now to integrate cosine phi over u, it seems like I have to use substitution, huh? The w equals to phi over u, so dw will be 1 over u d phi, is it right? Okay, the limit of integration, w at negative u will be negative 1, w at u will be positive 1. So now the integration becomes 1 or to 2, integral from 1 to 2, integral from -1 to 1, cosine w times 1/2 times the d phi becomes uw, right? uw, I'm sorry, do dw, udw, udw du. When I integrate that, that will be 1/2. I pull the 1/2 out. Integral 1 to 2 of u. Integral of cosine is sine w from -1 to 1 du. So that will be 1/2. But this will be 2 sine 1, huh? 2 sine 1 integral from 1 to 2 of u du. So that's sine 1 times 1/2, 2 squared minus 1 squared, 3/2. So that's 3/2 sine 1. Ugly. Yeah, bear with me though. Okay, bear with me. Now, notice that I actually spend more time in setting up than to integrate. Okay, in other words, don't think that you spend too much time with setting up. It is normal. Okay, with this, you want to make sure that when you do if you substitute all the ingredient of these integrals here, you want to make sure you don't miss anything. Okay, you want to make sure you don't miss anything. And yes, you need to draw, you need to sketch the graph, okay, the original domain, in this case R, and the one after you do the transformation. Okay, when you do your substitution, be careful not to use u anymore here, right? Because you may get confused. If you say u equals to phi over u, then you're done. Because the first u is different from the second u, right? Okay. I think that's where I'm gonna stop for this section. Do I want to do number 27? Oh, you know what? I want to do number 27. Let me write it down. So number 27, double integral of the region R, e to the x plus y. Let me write it down. Number 27, double integral of region R of e to the x plus y dA for R given by this inequality, absolute of x plus absolute of y less than equal to 1. R is given by absolute of x plus absolute of y less than equals to 1. I believe your issue will be, what does this look like? I think that's the issue. Okay, now this is how we will do it. Notice that we will use the following, I will use the following identity that we learned in pre-calculus. Absolute of blah is equals to blah itself if blah is positive or 0. Negative blah if blah is negative. Basically, if it is negative, you slap that with another negative to make it positive. Okay, so what happened then? It depends on when x positive or negative, the y positive negative. Further thinking tells us what happened in quadrant 1, 2, 3, and 4. In quadrant 1, the boundary becomes absolute of x plus, I'm sorry, in quadrant 1, x is positive, y is positive. This is the boundary. In quadrant 2, x is negative. In quadrant 3, both of them negative. In quadrant 4, the y is negative, which if we draw all these, the first one, x plus y equals to 1, will give us this. The second quadrant, y equals to x plus 1, it gives us this. The third quadrant gives us this. The fourth quadrant gives us this. Okay, so that's the region. That's the region R. Now let's do transformation. But I think the transformation already in front of us, because if you think about this, this is basically x plus y equals to 1. This is x plus y equals to negative 1. And this guy here is x minus y equals to negative 1. This guy here is x minus y equals to positive 1. That will be our transformation, right? So call that u equals to x plus y. The phi equals to x minus y. This will be what? Will this be t or t inverse? This is from bad guy to good guy. That's t inverse. Okay? But we know our good guy later on will be a nice rectangle, negative 1 to 1, negative 1 to 1. Okay? The Jacobian here will be 1, 1, 1, negative 1. That's negative 1 minus 1. That's negative 2. Jacobian of t will then be negative 1/2. But when we plug into the integration, it will be the absolute of the Jacobian. Okay? So that's why it is important for you to distinguish the absolute sign that comes from determinant and the absolute sign that comes from the absolute value. Okay, now this then becomes, that's the setup, double integral over region S. This is our region S now. E to the u times absolute of negative 1/2, absolute of Jacobian of t, dA in region S. Okay, which is integral from negative 1 to 1, integral from negative 1 to 1. I pull the 1/2 out. E to the u d phi du. Okay, so this is 1/2 integral from negative 1 to 1 of e to the u du times integral from negative 1 to 1 of d phi, which will give us 2, right? So 2 times 1/2, well, we basically get e to the u from negative 1 to 1. That's e minus e to the negative 1. Oh, the integration is so short. The integration is so short. If you set it up properly and correctly, then you will see things basically fall into its place. Okay? Yeah, but I think the hard part is like how to figure that out. You know. Okay, this is where I'm gonna stop for this section. Supplemental for 15.10.